In this lesson we present some analyses applied to a complex dataset. This dataset, discussed in the course on databases, consists of several sheets. Let's review the problem and how the data were collected. Patients underwent several visits and at each visit, several tests were performed. Data, anonymized, include information about each patient and each visit. We focus on blood tests, which are saved in the file bloodtests.txt. To load the data in R, we use the read.table function and select header equals true to also import the name of each column. Once data are loaded, we can inspect the first rows using the head function, which displays the first 5 rows. As you can see, the first 2 columns identify the unique visit ID. Furthermore, it is enough to print these first rows to notice that there are missing information. When a measurement was not taken, the not available, NA, string is reported. This is very common in clinical datasets as not all patients are expected to have a complete analysis of all possible markers. For sake of simplicity, we eliminate missing information. This can be done with the na.omit function, which deletes all patients without complete data. This solution is indeed suboptimal as we are discarding many data, which may still be valuable even if incomplete. Indeed, the process of handling missing data is generally not simple. Furthermore, we eliminate the first 2 columns, since we do not need the visit ID to perform statistical analyses. Once data are cleaned, we summarize all available columns using the summary function. To better visualize data, in the slide 5 columns at a time are shown. This step is very important since, at this stage, experts must check if values are reasonable or if they may contain errors. Let's consider a simple prediction problem, that is, we want to predict creatinine values using eGFR. This can be done with a linear regression model and, therefore, we use the LM function. We specify that our response variable, written before the tilde, is creatinine, and that we predict its values using an intercept, 1, and eGFR. After saving the result in an object called fit, we can print its summary. Looking only at the metrics shown in this slide, everything seems to be fine. The p-values are basically 0, meaning that we have a statistically significant effect of eGFR to explain creatinine, and the R-squared coefficient is 0. 48, meaning that using a single variable we are able to explain almost 50% of the variability observed in the data. In real-life problem it is an acceptable amount. Hence, is everything fine? To better inspect our result, we can plot the data together with the regression line. To this end, the regression line can be plotted with the abline function using the fit object as input. Look at the picture. Even though the diagnostic indexes are good, the regression line poorly fits the cloud of points. A linear relationship model is not suitable to explain the data, that is, we are in presence of nonlinearities. Therefore, we can fit a regression model of the form reported in the slide. The response variable, creatinine, is the linear combination of an intercept and the inverse of eGFR. By doing so, creatinine does not depend linearly on eGFR, but the model is still linear in the coefficients. Hence, it can still be fitted using a linear regression through the LM function. Looking at the R command, you can see that nonlinear terms are included using that specific syntax, that is, a capital I with the nonlinear term as argument in brackets. Again, let's look at the R summary. P-values are still equal to 0, but the value of R-squared is notably increased. To convince about the effectiveness of this data transformation, the scatter plot in the slide reports this time 1 over EFGR on the x-axis. We see a linear cloud of points which is perfectly fitted by the regression line. Instead, to show the nonlinear relationship, we can plot the data just as we did before, setting eGFR on the x-axis. However, since their relationship is not linear, we can no longer use the abline command, but we need to fit a curve. This is done using the curve command as reported in the slide. As you can see, the regression curve now perfectly fits the cloud of points, much better than our initial solution. Now consider a different problem, that is predicting the urea level using all other available information. We can perform this task using a linear regression model but with several input variables, called multiple linear regression rather than simple linear regression. The R command is again the LM function where, to specify that we include all other columns of the dataset in the analysis, we can simply write a dot after the tilde symbol. The regression is statistically significant, with a global p-value which is almost 0 and r² equals 0. 7, which is a very good amount of explained variability. Moreover, in clinical studies, it is common to also understand what are the most relevant factors. This is addressed by looking at the statistical significance of each variable, which is summarized by the p-value. For example, variable s_t is not statistically significant, having p-value equals 0.6663. Hence, we may consider to discard it from the analysis. However, instead of eliminating s_ht, let's eliminate s_hb. In order to fit the model without a single variable, we can use the dot symbol, followed by a minus and the name of the variable we want to exclude in round brackets. Looking at the summary of this new model, we note that the value of r² is basically unchanged, but, this time, the p-value associated to s_ht is below the 5% threshold. Hence, by removing one variable, a different variable that was not statistically significant now is. What is the explanation? The reason is indeed very simple, and it is clear once we plot the two variables. They are highly correlated, with a linear correlation coefficient between them equal to 0.9. Therefore, these two variables almost carry the same information, and the presence of a variable is masking the effect of the other. Is there a way to prevent and anticipate cases like the previous one? Yes, R provides a simple and elegant visual solution. This requires to install and load the CorePlot library. Then we can compute the correlation between any pair of variables included in the model using the COR function over the whole set of data. Finally, we can plot the result via the CorePlot function included in the package we just loaded, specifying the method equals ellipse option to get a better plot. Indeed, using this option, we obtain clouds with elliptic shapes that represent highly correlated variables, with positive, blue values, or negative, red ones, correlation. In both cases, it is better not to include both variables in the model, while it is enough to include only of them, the one you prefer.